Okay, everyone, welcome back to the Rust Embedded class with Professor Brad. Today is another good day to start again. This is day 2 of week 1, and we are going to cover some more concepts in Rust, and then we are going to go further. So I will give the grounds for Professor Brad to take over from here. Thank you, guys.
Hey, welcome. It's so exciting to see you all again. I'm here today at RustConf 2025 in Seattle, Oregon in the USA. I am very excited to be here. It's the premier Rust conference of the year, and there's going to be a lot going on. I might try after the break to move us downstairs so that people can say hi. I don't know. We'll try to figure it out. But because of that, things may be a little rough today. I will do the best I can to cope with kind of a weird setup on my laptop in my hotel room. But if we get disconnected, I'll try to reconnect as best I can. If that doesn't work out, I will make recordings for the rest of it, and I will have Mordecai, the Rust Africa folks, post those recordings so that we'll be able to see what's going on. Again, I'm going to do my best to watch the chat. Please, please, please make this interactive. Make it be a thing that we are doing together, not just me talking at you. There's no point in that. So I'm very excited to continue. We'll just basically pick up where we left off, I think, here in a moment, and that should be good. Let me switch for a moment to this and pop this up so that I can work with it. And let's go to, as always, the stuff that you're looking for is in the Rust Africa embedded repo on the at Rust Edu. And do join the chat at Rust Edu. I saw a lot of you joined the Rust Edu Zulip last time, and I would encourage you to do that again. But if you haven't yet, I can highly recommend this. And that will give us a place we can all chat about stuff, ask questions, etc. Join the Rust Africa embedded chat once you get there. So last time we talked a little bit about how to install and set up Rust. We talked about the very, very basics of Rust and talked a little bit about ways you could get started learning Rust. We're gonna sort of dive through the rest of Rust today. And again, this should be mostly a review. If you haven't started with Rust yet, or if you're just getting started with Rust, the Rust programming language is a good, freely available introductory text that you can use for getting started with the language. But I do want to just sort of review some of the basic concepts today, and then we'll try to take a look at our weird hardware. That'll be a thing we can do. So let me jump over and we'll pick up where we left off. Let's see. So what are we looking at today? So week 1, we got through references. I want to talk a little bit today about move semantics and ownership, which is a topic that didn't somehow make it into the outline. I want to talk about structs and enums, Rust traits, which is a big topic, and there's no way we're going to do it justice in the time we have. But there we are. Sorry, one moment, please. Too many windows. There we go. I'm going to put a comment in the chat just to make sure that, I see I'm in the wrong chat thing. That's why I can't see any of the comments. There we go. Sorry to have missed that. Yeah. Oh, the other thing I should be really clear about up front is that next Monday and Wednesday will be a week off on the schedule because I will be attending GoSim Rust Global in China. And so it's going to be really hard to figure out how to do that. So that'll give you a week to pick up your Rust if you don't feel like you're really there yet. So let's dive in and talk some actual Rust. Give me a moment here to change all the things. I'm going to switch to screen mode here. And everybody should be able to see the screen, and off we go. Let's see. So, whoops, wrong terminal. Drop this. Sorry, weird setup getting me here. One moment, please. I want this one. And off we go. All right. There we go. All right, let's do this thing. So like before, I'm going to set up a, yeah, this is going to be a problem. Let's see. I'm just going to shrink this window so that I can see what there are comments. Yeah, we're going to work in a small window today, I guess. It'll just have to be how it is. All right, because that way I can watch the comments. So let's make a day 2 directory. Let's fix the course outline real fast because, like I say, there's a topic sort of missing here, which is move semantics. Because that's going to be at the heart of one of the things that makes Rust special. We talked a little bit last time. Oh, there was one more topic too that we needed to deal with. Rust arrays. There we go. So that should get us going for today. And let's go make a new repository and talk about some code by writing some code. We'll call it that. That's as good a name as any. So, like last time, we've got a cargo.toml that describes how to cargo our build tool, how things are going to be built. And we have a main.rs, which helpfully has had a hello world placed in it that we don't want. So we will get rid of that, but we will leave the function main, and off we'll go again. So first thing I want to talk about is move semantics. And to talk about move semantics, we need to talk about Rust ownership and copying. And probably the easiest way to do this is for us to actually make a struct. I'm just going to make a Rust struct. And we'll just give it the uncreative name of S. This is how we declare structures in Rust. Rust has structures just like any structured programming language tends to do. This is a structure with no members. There's nothing in this struct. It is still nonetheless a valid value. Let's give it some members just for grins here. Let's make it be, I don't know. We'll call it object instead and give it a height, which is U64, just for grins. Who cares? So that's the struct declaration syntax for Rust, is that you say struct and then the type. This is going to be the type name for the struct. And this is a field of the struct named height, and this is the type of the field, which is 64-bit unsigned integer. So if I let Q be a thing, this is a struct expression, which is a new thing in Rust, is a expression that's used for sorry, one moment. I need to be able to join the chat here. One moment. Yeah, let's cancel that. I'm gonna go back. Oh, shoot. Well, shoot. I'm gonna close this. There we go. All right, so here's our object, and we just do the obvious thing, and it all works. And now that thing there is a perfectly good Rust structure, and this code should compile. And it does not, because, give the value, not the type. Duh. 12. There we go. Now it compiles just fine. And now we've got an object sitting in a variable. Again, we put the underbar here because we don't want the compiler to whine about it. And let's a little shortcut, a weird little hint is that if you happen to have a variable in scope that's the same name as the struct field, you can do this. This is a weird Rust shorthand that's kind of handy sometimes for making objects, and that works fine too. And that's fine. And if we try to println this thing, as one does, right? It'll be interesting to see if that should just work or if it does something weird. Object cannot be formatted with the default formatter. You might be able to use debug for pretty printing. So here's a Rust printing thing, as I can say : and that prints a value in debug mode, which shows, the structure of the thing. It's not intended to be used anywhere except when you're kind of debugging or messing around with the internals of stuff. But this still won't compile because the trait debug is not implemented for object. Add derive debug to object, or manually implement debug for object. So consider annotating object with derive debug. Okay. This is a Rust thing. This is what's called a proc macro, and you don't really need to understand proc macros except to understand, we'll talk about them more later when we talk about traits, except to understand that when I put derive debug on top of this struct, then it can be printed for debugging. That's all we really need to know right now. So let's compile this again, and it works. So let's run it. And when we run it, yeah, it's still whining about stuff, but there it is. It's object height 12. So now we got an object. Yay! Now the more normal way, of course, to use this thing is to print just the height. And then I don't need any fancy debugging. I can just print that because it's a normal number. And yeah, we use dots to reference structure members just like we normally do. And now it'll quit whining at us that the thing's unused, and it'll print 12. All right, everything's good. So far, everything, the syntax is a little different, but otherwise it's pretty much normal struct stuff like you'd expect in any programming language. Here's where things get weird, is we have a concept of ownership, and we have a concept of types that are not copy. So let's let's do this. Let's make a new variable r that contains q, which is a thing that you might want to do. And now let's see what's going on here. And we're going to get a compile error here, weirdly. And it's going to be a weird compile error, and that's going to tell us that we need to understand something more about Rust. Yeah, whatever. First of all, yeah, we'll get a compile error because I forgot the underbar, but those things happen. Here's the compile error we were interested in. Move a Q is because Q has type object which does not implement the copy trait. Value moved here. So right here in our program, when we did the assignment, something strange happened. You're used to, in every programming language probably that you've ever used, you're used to this making a copy of Q and storing that copy in R. That's probably what you're expecting to have happened. But it isn't what happened. What actually happened is it took the value, this Q here, and it took it out of here and put it in here. What's left in Q? Nothing is left in Q. Q is now useless. It is, it's been moved out of, and it doesn't contain any value. And the compiler knows this. This is part of what the borrow checker does. So the compiler is going to be all, no, you can't be doing that. That's not okay. Notice that it says I could clone the value. What if I want to make a copy? Well, one way is that I try to clone the value, and now it's going to complain that clone isn't implemented. And so you need to implement clone. And the way you implement clone for this struct is the same way we implemented debug. We just derive the clone trait. And now that we've done that, this code will compile and run just like you expected it to, and print the 212s just like you expected it to. So what's going on here? What's going on here is a fundamental rule of Rust. And that rule says every value has a unique owner. And that means that if you want to work with two different values, this Q struct and this R struct, you need to have two owners for the Q and the R struct. That's just a thing. So what if I want this to work? Can I make it work? In this case, it turns out I can make it work by deriving the copy property for the struct. Because we can copy U64s, they're copied by default, then we're allowed to say that it's okay to copy objects, and this code will work fine too, and we're all good to go. Now, notice what it means when you make a struct copy. It means that every time you do this assignment, you get a copy of the whole thing. Sometimes that's impossible because there's some kind of value inside the struct that itself isn't copy, and then the compiler will stop you. Even if it's possible, if this struct contains something giant, it's probably a bad idea to just casually make copies of it. So you probably don't normally want to do this. You do this, and if you want to make a copy, then you explicitly say you're making a copy like this. That's best practice for Rust. Notice that once an object is moved, all its references go invalid too. This won't compile. Now I've got a reference here, and because I have a reference, shared reference, well, maybe this will be accessible. I don't think it will, though. Let's try it, see what happens. But this definitely won't compile. Well, let's just copy this bit out for a minute and see what happens here. Oh, it's okay with that, right? I couldn't remember what the rules were exactly. Oh, because QR is unused, right? This will work fine. It's like, yeah, okay, whatever. And now if I uncomment this, it's like, no. Right now, you've got a reference to this thing, right? A thing that is like a pointer to this thing. But I tried to move it while I was still holding that pointer. I'm going to use this pointer down here. And so it has to be good when I get down here. And so the compiler is like, no, you can't be moving out of a thing that you're going to use a reference to later. This is one of the most important differences between Rust and C, right? Or C++. C and C++, you might get a compiler warning, but you won't get an error, and you'll be lucky if you get a compiler warning. A lot of times this kind of thing is just silent. The compiler's like, sure, I'll do whatever you told me to do. And because you have copy semantics, it mostly kind of works, but not always. This is a classic source of memory fail. And this is exactly what Rust is trying to do for you here, is have you have tight control over your memory and catch your memory errors at compile time rather than at runtime, which is kind of too late. So that's Rust ownership, and it's also a little bit about Rust structs. Like I say, Rust structs are mostly fairly vanilla. There is one other thing you should know probably about Rust structs offhand is that there's also what's called tuple structs, which have anonymous parameters like this. You run into them once in a while, which is the only reason that I bring them up. Tuple structs are just like structs, except their fields have the names 0, 1, 2, etc. Let's do this. And then, so that makes a new tuple struct. It's just like a struct, except that, like I say, the names are different. This is r.0 is the first field of that tuple struct. And this should compile and run fine, and it does. And you can see what's going on there. So there's Rust structs. They are kind of interesting. Next, let's look at Rust's enums. And people, let me know if you have any questions or anything. I'm not seeing anything happen in the chat. I'm assuming that's because nothing's happening in the chat. But if I'm wrong, let me know. All this clear? Everybody X up in chat and tell me that this whole thing's clear and that you're all with me so far. All is good. Okay, perfect. All right. Thank you. I like to see when people are doing stuff. All right, let's talk about Rust's enums, enumerated types. C and C++ have enums. Python doesn't really have enums. There's no real difference except syntax. This we use between tuple structs and normal structs, except syntax. We use this in situations where we just don't want to make up names for the elements of the struct. And so we use this sort of simpler syntax. But other than that, they're exactly the same. They act the same. It's kind of a weird addition to the language, and I have my doubts about whether it was a good idea, but we've had it since the beginning, and it all works. So enums. C and C++, we have enums. I think in the latest Python, we have enums. Java may have some kind of enum type. I don't even remember. It's been so long since I wrote a lot of Java. But our Rust enums are kind of special. They're like Haskell's enums. They're what's called a sum type or disjoint union type. And they are a weird type that has its own stuff going on. So, but it's really, really useful. Usually we use a color enum to illustrate this, and you can have them be just like normal Rust or C or C++ enums. Now I've got an enum that can have one of three possible values: red, green, or blue. And down here, I can make an enum value. And you'll notice that unlike in C or C++, I actually have to qualify this red with the color red. I have to actually say what enum it's coming from. That's a little bit weird and annoying, but it does make things clearer. And now if I println this, I get what you think I do, except that I don't think this will compile because I don't think these things print by default. Yep. It's like, no. You can only debug print these enums, so that makes sense. So let's do this. Now we're debug printing, and here we are. We've got an enum color. It's warning us that we don't use green or blue, and that's very nice of it. But at the end of the day, it prints red just like we think. So why is this useful? Well, first of all, it's useful because like the switch statement in C and C++ or Java, Python doesn't have a switch statement, which is really annoying. I have the match statement here. And the match statement in Rust is just stupidly powerful, and you use it all the time for everything. It is absolutely awesome. It does what's called pattern matching, and we'll work up to this sort of by degrees. Let's say if it's color red, it's red. So that's the syntax. Here's the thing, the value that you're trying to match. Yeah, it's very similar to switch case. It is, except awesome. Everything that's terrible about C++'s switch, this thing gets right. Like I say, it's heavily borrowing from Haskell and other functional languages here. So this is the thing you're trying to match. This is what happens when you match. And in this case, what happens when you match is we print this thing. So this should work fine. Oh. So one of the requirements of Rust's match statement is you can't leave anything out. All the cases have to be covered. It's like colors could be green or blue, so you'd better tell me what happens if this doesn't match. There's no, like, it doesn't just fall through. It actually insists that you match something. So the easiest thing, if I do want a default value, is I can just do this, which is a very strange looking thing. This thing on the left is what's called a wildcard pattern. It says match anything. So it tries the matches from top to bottom. It tries the color. If the color's red, it does this and it's done. Otherwise, it gets here and it says, well, this matches anything we haven't matched yet. And in that case, what do? Well, we just return a unit value. So one of the secrets of this is, remember how I said earlier that if statements have values? match statement, if else statements have values, match statements also have values. So this just says return the unit value, the value that means nothing happened. And so this will compile now and work, and we'll get it's red. But notice this, it's got your back here. If you forget a case, it's going to tell you. And notice that this pattern matching is kind of sweet. It means that I can, it turns out the pattern matching is very, very powerful, and we'll see in a second how to use that. By the way, this thing with an expression and a comma is one choice. Another choice is to do this, and Rust doesn't require this because reasons. This will actually work, I think. Yeah, it should. Yep. So you can have block structure for these things if you want to too. And a lot of people really prefer to just always do this. But the other thing's a nice shorthand sometimes. So I said Rust enums are awesome. They're partly awesome because they're really well integrated with match statements. But let's show the way in which they're really weird. Let's use a tuple struct here. Any F32, F32, F32. So we'll have 3 floating point numbers. This is now what's called a value carrying enum. That is, I can say the color's red, I can say the color's green, I can say it's blue, or I can describe the proportion of red, green, and blue that I want to have my color have. So now this enum carries data around, which is a thing that you can do in most functional languages, but almost never otherwise. How does that work? Well, let's go down and look at it. And here we'll have what's called pattern variables. So I'm going to just make pattern variables that match the stuff, right? We know that there's 3 F32s being carried around by this any variant. And so I want to know what I want to give those names so that I can actually refer to them. And that then let's say, and by the way, Boolean expressions are just like in every other language these days. So I'm not going to explain any of that. Let me know if you need an explanation. So if the red component is bigger than both the green and blue components, we'll say it's reddish. And otherwise, we won't say anything. So now, I am good here, and this should compile and run. And let's actually put the actual components in here, right? So that we can see what's going on. Let's run this, but then we don't have it being reddish, so it just says it's red. But let's fix that. There we go. And now when we compile it, it says it's reddish and tells us the components. So that is Rust enums. And again, you know, the enums can have tuple patterns. I could also do this, and I probably would do this in this case to get myself names for these components. And now down here, there is pattern matching syntax for this. But yeah, let's use it. And now I can write like this, and that should actually be okay, I think. I can never get the syntax quite right. That's why I was... Oh, right. When I created the color, I didn't do it right. Right. And that's why we want to give these names sometimes, is because we want to make sure we keep track of which one's which. And now it's perfectly happy. And we've got, oh yeah, it's reddish. And there's the color components. Rust bonus trick here, because we have time for it. It turns out that you can have conditionals in the match statement itself. So I could actually write this like this, which is nice because now I can do something completely different if this isn't a reddish color. I could, for example, say, now I could have a separate match statement for bluish colors. Sorry, greenish colors. And it would be perfectly cool with that. So now we'll make our color greenish. And when we run it, we'll notice that it's greenish. So we're all good. That compiler warning's bothering me. Let's look at it again and fix it. In this case, I mean to do this. It's warning me that this thing isn't true. Notice down here, it's telling me what compiler stuff made it whine at us in these warnings. Here's a thing you can do, and you shouldn't normally do this, but in this case, I'm going to do it. This says that, and now it shuts that warning up. I'm aware here that I'm not using all the variants, but notice that if I don't do this, then Rust is, there again being cool and saying, you have these variants in your enum and you're never using them. What are you even doing? That seems like a terrible idea. But you have two choices. You could get three choices, right? I could get rid of these enum variants I'm not using, right? I could use them, which is probably what I meant to do since I added them in general. Or I could do this and shut the compiler up. And I would really recommend being cautious about this, but in this case, since it's just a toy demo thing, that's what we do. So I think this is a good spot to take a short break. If people are cool with that, let's take 5 minutes, and at 9:45, unless people have questions. Anybody got any questions up to this point? Anything we've missed discussing that you wanted to discuss? Going once, going twice. All right. Yeah, the compiler really does try to make you write good code. It encourages you strongly to write good code. And if the code's really bad, if it can tell that it's going to break and it's pretty good at that, it'll just be like, no, I can tell this is going to break. That's a really different philosophy than some other programming languages we could name for sure and certain. All right, I am going to add a new scene. And so let's take 5 minutes and we'll start again at 45 minutes after the hour and pick up the next set of topics, I think, that we need to tackle. So one moment here. All right, talk to you in a bit. Let's see. Okay. And there we go. All right. Back in a moment. All right. Let's go try to find in the restroom. Make some more coffee. All right. Forget that piece of equipment. All right. That's frustrating. I went for that 3 times and then did not throw it in. That was so weird. Oh, there's this thing I can use for my coin protector, my card protector. A lot of things for sure. That's certain. Well, I guess I've lost that. Oh, I can just. That piece of equipment, I would have a lot of bad trouble. All right. So it's not actually in my bag. A lot of shit in here. Super annoying. I don't understand. All right, stuff happens.
Hello, Professor. I think we are about done.
Yeah, one moment, please.
Okay.
Sorry. Oh, yeah, I think we're ready to go. Sorry, I was looking for a piece of hardware I thought I had, but do not, in fact, have. Let's get going. All right. So, yeah, that's some more of Rust. Let's take a look at another couple of Rust topics, and then maybe it's time to actually poke at some actual hardware for a moment just to see what it looks like. So yeah, you've seen sort of some Rust. No, it's just my webcam right now. Thank you though. We've seen some Rust. Let's next look at just a couple more Rust concepts. There's just a couple more things we need to look at, and then we'll be ready to actually start talking about the stuff we actually care about. So let me flip back to the screen here. Now you should be okay. And then we will go ahead and put a little more code in here. And that's Rust arrays is the next thing, I think. Rust has arrays, just like all programming languages in these modern times have arrays of some kind. Hopefully everybody's comfortable with the general idea. But Rust arrays are special, just like most things in Rust are special. Let's make an array of integers. So now A is a variable whose type is an array that holds 3 U32s. Now this is important. Unlike every other language you've ever used, I suspect, the size of an array is part of the array's type. So when I declare an array, I don't just declare what the element type is, in this case, 32-bit integers. I also declare how many of them. This is absolutely a thing. And if I try to do this, Rust is going to be completely unimpressed by my plan to put 4 integers in an array that will only allow 3. By the way, cargo check is an alternative to cargo build that just runs the part of the compiler that checks that the program's okay. It doesn't generate code, so it can be a little bit faster. People use that quite a bit. So yeah, it's like, no. You told me you had an array of 3 elements. You gave me 4 elements. So this is an array expression. It evaluates to an array with the square brackets around it. I can also write another kind of array expression I can have is something like this, which just says put 3 3s in the array. Obviously, if this is 1024, then probably this is going to be better than listing 1024 3s. And this will compile fine. But if I have too many or too few elements, it won't work. The other thing is that array types are copy if their elements are copy. So part of the reason this works is because 32-bit integers are a copy type. If I try to make an array of our struct, we called object, I guess, T object. This part's legal. Yeah, we're not copy. And so this is going to, I think, fail on me. Yep, saying, copy's not implemented. You can't do this. You might want to just make it copy, or you could try to put an inline const block, which is super weird. So the point is, Rust arrays are a little weird. But yeah, I'm trying to think if I want to introduce closures today. Probably, but not right this second. So let's make this array mutable and write the obvious thing. Yeah, definitely. The course outline is available. So we'll do the obvious thing here, and then we'll print a sub 0 and a sub 1023. Now let's make a mistake here. Let's print a sub 1024 and see what happens. Notice there isn't any 1024th element, right? These elements go 0 through 1023. So this is actually a programming error. And we should see something happen. And it's like, well, first of all, it's like maybe you should fix your types. So that's not too surprising. It's like, second problem is expected U32 found U size. That's super freakish. I don't understand. Oh, because indexes are like that. Right. So what's happened is type inference here has caught us. It turns out that the index type has to be a type called usize, which we haven't talked about yet. There are 2 Rust integer types that are special, usize and isize. Usize is the size of indexes on your machine. On this machine, it's U64. On the computers we're going to be programming for this course, it's U32. So it's a size that changes. It's an integer of a size that changes depending on the processor. isize is the same, except it's signed instead of unsigned. So when this thing says sees I here being used as an index, it's like, well, then I must be of type usize. And then we try to assign a usize into this array, but the array is an array of U32. So there's 2 ways to fix this, the easy way and the hard way. The easy way is just to make this be this. But the other way is to Yeah, you can do what you want to do. Pull requests for the repo, I think, are welcome always. And then, so what we'll do here really is just this, and that'll shut up the compiler error. Now let's see what, oops, maybe it'll shut up all the compiler errors. We'll see. Whoops. I don't know what's going on here. There we go. And now it compiles just fine. But it compiles just fine. So what's going to happen when we run it? That seems really bad that it compiled just fine, because we know we have a bug here and the compiler hasn't noticed that bug. I'm actually kind of surprised the compiler hasn't noticed that bug, but it hasn't. So let's run it. Oh, look at that. When we ran it, oops. Oh, never mind. The compiler did catch it. It only caught it when we tried to compile it. Cargo check didn't catch it. It's like, this would panic at runtime. So let's allow unconditional panic temporarily. This is a terrible idea, but it'll let us see the behavior. So we'll shut up the compiler being too smart and noticing that we're about to make a bug, and we'll make a bug. Whoops. Whoops, whoops, whoops. Interesting. All right. The compiler really is not interested in letting me make this bug. It would be really happy if we did not make this bug. And look at that. We talked the compiler into letting us do this. Now, what would happen in C and C++ at this point? Well, you'd get whatever was on the stack beyond the end. There's no checking being done here. It's just like, yeah, sure, whatever size you want. Not Rust. Rust checks all its indices at runtime. So here, instead of just some weird value or error, it's like, no. At runtime, when we ran the program with cargo run, it's like, no, this isn't a thing. Your index is out of bounds. This alone catches a billion errors that C and C++ don't catch. It's really common to walk off the end of an array in C or C++. Here, the compiler tries really hard, just like the C and C++ compilers actually try pretty hard to keep you from making this mistake in the first place. But if you do manage to get it past the compiler, the runtime still has your back and says, I bet you meant 1023 here. So let's run this now. It's perfectly happy, and it's like, yeah, 1023. Okay. Actually, we should add 1 to this value so that it's more interesting. There we go. 1 and 1024. Okay. So that's Rust arrays, more or less. Unlike C arrays, C and C++ arrays, array types are copy if their elements are copy, and their move semantics otherwise. And that matters when I'm working in with functions. So let's make a function here. Oh, by the way, it's really bad practice to just type these things over and over. It's super error prone. Rust has type defs. Let's use them. There we go. So this is just gives a name to that type, like that. And so now we can say our show array is a better name. I just saw a quote of Uncle Bob Martin saying you should name your variables with the same care you name your firstborn children. I thought that was absolutely silly. I name my variables carefully, but not that carefully. So let's just run this and prove that it actually works. It does, and it does the same thing we did before, but here's the interesting part. We'll make this array mutable, and we will change a sub 0 equals, I don't know, 1025. I don't care. So what's happening here is that this array, we own this array. Who owns this particular value? We do here in the function. And that array is living on the stack. It will be freed when we leave. And so this change I just made is very local to this function. If I call show array twice down here, oh, sorry, I should just do it. I should do some value that matters. Right? You might expect that this will print 2 and then 3, but it won't. It'll print 2 and then 2, and that's interesting. It's one of those weird little things. What that means is that when I did this, this call made a copy. It made a copy of the array, which is way different than C. Literally all 1024 elements were copied into the function, which then owns a copy. And that is weird. And it's not what you expect from C and C++ or Python or really any other languages. They generally pass things by reference. Well, we can absolutely do that in Rust, but it's not going to work quite like you think it does. If I do this, then I can do this. But then what's going to happen here? Can I assign to this? No, because I have an immutable reference to it, right? I'm not allowed to change it. This mute doesn't do anything anymore. The compiler won't even take it. It's going to be like, this is a, it'll let you mute the pointer, I guess, but nobody cares. This is not going to work because I'm going to get a thing saying, no, you can't mutate that. You don't own a mutable reference to it. You only own an you don't own an exclusive reference to it, so you can't do this thing. So this will compile fail. And it's like, yeah, you might want to make that mutable so you can mutate it. And so we'll do that. But now when I go to call it, that's going to fail because I didn't pass it a mutable reference. It's like, you probably should pass it a mutable reference. All right, well, let's do that thing. And now it's going to be okay because I declared the array as mutable, which means I'm allowed to pass a mutable reference. And then I pass the mutable reference here again. And this time it doesn't copy the whole array into the function. It just gives a temporary exclusive reference to the array to that function. And that's fine. That makes everything golden. And now I'll get the behavior that you might have expected from C++ when I run this, which is that each time I do it, it'll change the array. But this is part of Rust's superpowers, right? Is that it checks this stuff at you. It's really careful about saying, if you want to be able to write something, then you need to set it up so you can write it. And you'll need to know that you're writing it, right? I can't make this kind of a mistake where I think that I don't need to, that show array won't do anything to the array, right? It looks like it won't do anything to array. It's called show array. I can't make this mistake. It'll be caught at compile time, and the compile will be like, no. Show array needs to be able to change the array. You don't understand how any of this works. One of the things that makes people hate Rust when they're starting out, one of the biggest things that makes people hate Rust when they're starting out is this idea that the compiler unlike the compilers they're used to, just keeps complaining. No matter what code they type, it's like, no, you didn't want to type that. That's terrible. This isn't going to work. This is a problem. This has a weird problem you barely understand. I love that about Rust. And the programming language Nickel that Keith Packard designed with a little help from me over the last 40 years has the same property, that it tries whatever possible to have the compiler complain. Because that's what if the compiler complains and then you fix it, your program is more likely to work at runtime. We want to catch errors as early as possible, and that's a fundamental principle of programming languages. And Rust is really, really tuned to catch your programming mistakes as early as possible, because then when your code compiles, it tends to work. Haskell is very much if it compiles, it works properly kind of language. Rust is almost as good in that regard. It's a lot easier language to program in. When you write a Rust program and the compiler doesn't complain and Clippy doesn't complain, probably when you run the code, there'll be few surprises. And the best surprise when you're programming is always just no surprise. You don't want any of those. Darn it. Sorry. Messed up here. So that's probably all the type stuff. I want to show you one more little thing, unfortunately, that you're going to have to care about, which is closures. Rust has these special functions. Remember how I said that when you declare a function, you have to provide the argument types, and you have to provide the result type. And this functions in global scope, just like it would be in C or C++. Unlike C or C++, I can also move this function here. That is absolutely legitimate, or even down lower, closer to where it's used. Let's put it down here. This is legal in Rust. Almost anything that you can put at the top level in Rust, you can put in the inside of a function in Rust. It's very, very liberal in that regard. Oh, sorry, I forgot to switch back. Oh, I'm so sorry. Thank you. I see why there's a problem here. All right, let's try that again. So what I did is I took our show array function and I moved it inside our main function, because I'm allowed to do that. And I moved our type definition inside our main function because I'm allowed to do that. So this will still compile and run just fine. Rust doesn't care where you put stuff. But this is still really a global function secretly. It still is really being just compiled at the top level. And I still have to give all the argument types and that kind of stuff. It turns out that Rust has these special functions. And by the way, functions are a value. Functions have a value in Rust, just like they do in C and C++. So I can say, something like let f equal show array. It's perfectly happy with that. And all the type checking will happen and stuff. And I can do this. But this is secretly just a function pointer to a global function. There's no object here. Let me show you the cool thing you can do. I'm going to put this back just for grins. You can... Time is it? Oh, man, I got to get going here. All right. So this is the other way you can make functions in Rust. And that's with what's called closure syntax. So this is a Rust closure. it is a function, but it's a function that is sort of special in that it lives on the stack and is an object type like any other. And you'll notice that one of the features of closures is that it'll do type inference. It should figure this out. It might not. We'll see. It does some type inference. It's not always good at it. It's like, yeah, I don't actually know what you're doing here. All right, so... And we'll make that be that. And now we'll be all right. But normally, for simple stuff, it'll do that. The other thing about this is that, like I say, it's a local function. It means that I can refer to variables that are in scope. So the other way to fix this, the other way I can do this now is because I can refer to variables that are in scope, I don't actually need any arguments. I can actually just do this. And I can refer to this variable out here inside here because it's in scope for the closure. That's something functions won't let you do. And so now I can just change this to nothing. I don't need you. And now it works. Nope. You know why? Well, first of all, because there's this weird mutability thing where if I'm changing something inside the closure, I have to make the closure variable be mute. That's annoying. But the bigger problem is that when you declare this closure, it takes ownership of A. And because this closure owns it, nothing else can touch it. So after the closure takes ownership of the array, this for loop's not going to work. So I need to move this down here. So now we're good, except there's a warning. Type alias demo array is never used, which is inarguable. So now we got a closure, which is kind of cool. This is just a convenience mostly, but it's used quite a lot. For example, we can actually replace this for loop with core array from fun. This is Rust's module system. Core is one of the libraries that's in scope in Rust that contains stuff that's like everybody can use for anything. Array is a module in there, and from fun is a special thing here that lets me write this. So that here is a closure just being used as a function argument. And this is really common in Rust. And is, maybe a little cleaner than writing a for loop in this situation. And Rust is fine with that, except that it notices that this initial assignment is never read, right? So let's get rid of it. And because we're on a narrow screen, I'm going to do this, even though it's probably not great formatting. And now it's perfectly happy. And it's like, yeah, sure, this is a thing. So those are Rust closures. There's a lot more to say about Rust closures, and I'm not going to say it because we'd be here for another hour. But you at least get the idea that these closures exist, and we'll be using them occasionally as we actually start to do embedded programming, so you should know about them. All right, we got 15 minutes. That's enough time to do a couple of things very quickly. Probably the first thing is I want to use this core array from fun as an excuse to mention something I realized I forgot to talk about, which is Rust's amazing documentation for its libraries. So let's switch to a browser window for a moment. And apparently my face went away. I think we can all live with that. And then let me get this browser open. And we'll go to Rust core array from fun. Let's just Google for the document we want. From fun in core array. This is the Rust documentation. Let me make the text bigger so you can actually read it. Maybe. Rust doc is a key piece of Rust. You can put doc comments in a thing to make this documentation automatically. It's a doc comment system, just like a million other doc comment systems, except really, really well done. And you'll notice that this is documentation of the core library. There's 3 different libraries that are shipped with Rust. The core library is one. Rust doc_rested. The standard library is another. The Rust standard library has a whole bunch of stuff in it that is just amazing and fantastic. And unfortunately, what we're going to do is ignore it because we aren't allowed to use it. Because in bare metal programming, the standard library is huge and really depends on having an operating system. And we're not going to have an operating system. So we're kind of stuck with the stuff in core. The third one is alloc, which is the same problem. So we're stuck with stuff that appears in the core library, but that's okay. There's good stuff in there. Let's actually, for a moment, and I highly recommend whenever you're working with anything in Rust, look at the documentation. It's really good for almost everything. Great documentation system. So let's go find my window again here. There he is. How do I get this guy out of the way? Sorry. I really like my home setup with 2 screens. It's so much nicer. So let's talk a little bit about that. That's probably the next thing to talk about, unless people have questions about any of this stuff, in which case, please speak up. What the next thing to talk about is probably what do we do with what's bare metal programming? So I showed you last time, I think, the computer we're going to be working with, the microbit, which is just a dumb little microcontroller that has very little memory and very little anything, really. And so we're not going to be able to put the standard library on that thing. It turns out that if I want to not use the standard library in Rust, it's as simple as typing this weird little declaration. This is a directive to Rust to say, don't link against the standard library. Don't use it. Let's see what breaks. Because a bunch of stuff's going to break. Let's see where we're using the standard library. Oh, no, println is part of the standard library. It depends on an operating system underneath to do printing. So we're going to have to not print things in our programs unless we can figure out some other way to do it. What else is missing? Oh, nothing. I mean, there's this weird panic handler is required but not found thing. But other than that, everything we've done up to this point apparently is okay with thingy. Now, clone is going to be actually a problem because we don't have an allocator. So I'm kind of surprised that didn't complain. But other than println and clone, this stuff is all perfectly good no-std Rust. Now, those are pretty big other thans, and we should probably figure out what we're going to do about that, and indeed we will. But the point is, it's not a huge deal that we are living without no-std. We still have most of Rust available, without std, we still have most of Rust available to us. And this is probably the point at which we want to actually switch to doing microcontroller stuff. But I'm kind of thinking we might just end a little early today and pick this up again in a couple weeks when we actually have everybody has their microcontroller and they've had a chance to catch up on basic Rust. Let me grab something really quick, just a moment. Where are you, little board? So, to remind everybody, let me flip to my fancy cam here. Come on, OBS, you can do this. .cam. There we go. There's our little board. I'm going to go a little closer, and then I'll hit its autofocus button until it autofocuses. There we go. That's our little board, the microbit. I'm going to turn off this light. I think it'll actually be easier to see. And the microbit is, like I say, this is the back side. The front side has these lights and buttons and that kind of stuff. The back side of it, so this has got 2 buttons. It's got an LED array. It's got a touchpad. It's got a microphone. It's got a speaker. And it has an edge connector for stuff. It also has an accelerometer and magnetometer so that it can measure acceleration. It can measure like a 3D compass. It can measure direction, compass direction. So it's a pretty fancy board. And on the back, you can see the speaker, which is this big blob in the middle. You can see the actual microcontroller, which is this little black square here. Let me turn on the light for a second. Maybe it'll be easier to see. Yeah, this little black square here is the microcontroller. This thing over here is another little microcontroller that's just as powerful pretty much as the first one. And that one's just used for controlling everything. You will never touch that one. It's just got firmware and stuff on it because modern electronics is weird. This is a fun little piece of hardware. There's a lot of cool things you can do with this. Let's go look real fast in the last couple minutes at what code written for this microprocessor looks like, and we'll talk about a few things about setting up to program this. We're not going to try to run anything today because my setup is too jank, but we'll run it. Next session. So let's go look at some code. I think I have that stuff here. Yep. Here's a piece of code written for the microbit. It's not a perfect piece of code, but it's a piece of code.
Please, you're not seeing your screen. Sorry.
I forgot to switch back to the screen again. Okay. Sorry. Thank you. I'll figure this out eventually. Too many things going. All right. So here's a piece of code written for the microbit. By the way, this repository, I think it's linked maybe from the thing, from the README on our repository. This repository, PDXCS Rust Embedded, has all the code I use when I teach a 10-week Rust Embedded course at Portland State. So you can look at any of that you want for examples. This is one of the simpler ones. First of all, let's see how it's set up, because it's set up kind of an interesting way to begin with. Notice that our cargo.toml, the thing that tells cargo what to do, has suddenly gotten way fancier. The first thing is that it's got a dependencies section now. This says what libraries to grab from crates.io. Actually, let's go back to the browser for a minute. So let me figure out how to do that. Always hard. Browser. Let's go to crates.io for a moment, because this is another one of Rust's superpowers here, is this. This is where people put library crates that they want other people to use. These are all under some open source license and are freely available for people to play with. And one of the interesting things about the Rust embedded community is that those crates for embedded are actually just in with everything else, and there's a bajillion trillion of them. For example, we're using the Cortex M crate. Here's the Cortex M crate, and you can go to its crate documentation by just clicking on this, and now we're in the Rust doc for Cortex M. And let me switch windows again. And if you look here, what you see is that this line here says use version 0.7 of the Cortex M RT crate. It doesn't actually use Cortex M. Oh, yeah, it does. No, it doesn't. So this thing just can use those crates from crates.io. And when I say cargo build, this is really old code, but it'll still work, I think. That's another one of Rust's superpowers. It's warning me that some of the dependencies are out of date. Don't care. When I build this, it just goes and gets the crates that it needs off crates.io. Cargo just is like, yeah, I know how to do this. And that's all we needed was that little bit of code in cargo.toml to actually make this work. And that little bit of description in cargo.toml, and that's it. The features we'll talk about later. It's a whole concept. The other thing that's making this work is this, which says, oh, when you build this, don't build this for the computer you're running on. Build it for this other computer. This is an ARM processor that's on our little target machine, on the microbit. And so when we compile, this is how hard it is in Rust to cross-compile for a different processor. Man, in C or C++, that's nightmarish. In Python, it doesn't even make sense. And Java, it doesn't even make sense to cross-compile. But in C and C++ and Rust, where it does, Rust is just like, yeah, just say what you want to build for. It's fine. That's literally all I needed to do. So now we've got our program. If I look in target thumb v blah 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 / release, there's Blinky 2. There's our program. Well, what does the source code look like? Let's look at that for a second. You can still see the screen, right? We're on the right page. I need to check real carefully. Yep. Let's look at Blinky 2's source code, because, of course, that's interesting too. No main, meaning we don't really have a main program. We have a weird entry macro that defines main. No std, just like before, we can't use the standard library. This uses some stuff from some of the libraries that we've pulled in. That's what these use statements do. This sets up our alternative to println that we're going to use. Then we just grab the hardware and we just write this little loop. This is the whole program. This is all the more there is. Most of the hard work of dealing with weird hardware is being taken up by this board support crate and this HAL crate. And so when I run this, it's going to turn an LED on, it'll wait a little while, it'll turn the LED off and wait a little while longer. And when we do those things, then that LED on the board will blink. And there's no operating system involved. There's nothing involved except bare metal rust. So that is where we're going. And starting next session, remember, we're taking next week off while I'm in China. But starting the following week, when we start again, we're going to leave the world of programming for our laptops and desktops behind. And we're going to move the world to the world of programming for our microbit. And we'll really dive in and mess with that stuff. So that's what I've got for you today. I think we're out of time, and that's good because we're also out of time. I don't know what just happened there. Let's go back to the webcam view. And thank you very much. It's been huge fun. Is there anything else we should talk about before we go? Going once, going twice.
Okay. Thank you very much, everyone.
Thank you.
Thank you very much, Professor Brad. It was really nice having you guys. And please, let's keep informed that next week there won't be class. And our class is always Monday, 5 p.m. GMT +1, and Wednesday, 5 p.m. GMT +1. And there won't be class next week because Professor Brad will be in China. So upper next week, that's when we are going to start our next class, and then we are going to start programming with the microcontrollers that will be available to everyone. So everyone, see you upper next week, and stay in tune, stay informed. Follow Ross Africa for more update of when the class is going to hold. And thank you very much. Bye-bye.
Bye.